All right, now we get to the meat. Our goal is to be able to write explicit and recursive routines for arithmetic sequence. I'm just going to a little plus sign here, just to let you know arithmetic sequence have to do with addition rules. All right, so I can write that. It says a sequence is and. I love it when they say and. I'll let you know that this is going to be a vowel, doesn't it? Ordered list of numbers in which each number in the list is called a term. So the domain is a subset of the integer input. That means we're not going to use any decimals when we have an input in there. And the range happens to be the terms. So if I input 1, out comes my output. That's called a term. All right. And arithmetic sequence, which is really just a linear function, right, is a sequence for which the consecutive terms have a common difference. All right. So it's new, somewhat new, but it's not really hard. All right. So if you look here, the terms of the sequence we started talking about, and you can tell this is the first one, right? It was 0, 7.5, 15, 22.5. That was what we just got done doing, the steps on the way up. To get our difference, we can take any term, 30, and subtract the term in front of it, 22.5, and we get our 7.5, right? And honestly, 60 minus this is 7.5. 7.5 minus 0 is 7.5. So the difference is 7.5. That tells us how much we're changing every term, right? What is the common difference of a term in the sequence from what we explored before? Well, those are just these numbers. It's talking about from the top. And if I just wrote a few backwards, like from the top down, 97.5, 90. Well, if I take any of these and I subtract the term in front of it, that is how you get a difference. So this minus this. And in the second one, the top staircase coming down, it was negative 7.5. So going up, right, the bottom, 7.5, going down from the top, negative 7.5, that's the change that's happening every step. That's all your difference is. It's your common addition rule. All right. So when we write them, you can write different rules for a sequence depending on the integer you use as a position number of the first initial term. The most commonly used starting positions are 0 and 1. Totally true. All right. Explicit defines the term position n as a function of n. This is what we're used to. Kind of let you find any equation you want. And recursive defines the position n by relating it to one or more previous terms. So that's saying we have to know something before we get our next one. And I'm going to show you a couple. All right. So if you look here from the bottom, the very first thing you do is you realize that you started at 0 steps. All right. And as an explicit function, you have your start and then your rule per step. All right. And as a recursive, this is your start, and then your rule happens down here. All right. So this is pretty much a linear equation, right? My y-intercept, my slope, and then you define how many steps there are. If I started on the first step, right, all that does is it says, hey, don't apply your rule until you get off the first step. That backs everything up. We'll talk about this a little bit more. And it says, hey, we're still taking 14 steps, so if my first term is 1, I have to go all the way up to 14. This is going to sound confusing. When you see us use it a few times, it's going to get a lot easier. Now, recursive does something else. It tells you your starting point, and then it says, hey, to find any step, start with your step before that, and then add your rule. All right? So let's go ahead and think about this in terms of the top steps where we're reducing. So I would say for this one, my function related to the number of steps I take is equal to my top step, which I believe was 105. Let me check. Looking at my sheet, it was 105. So I start at 105, but then I go down 7.5 every step that I take. And for this one, right, we would still take from 0 to 14. It says, hey, let's call that starting position 1. Well, how would that change anything? Well, it doesn't change a lot. If I just say, hey, well, let's start on the first term instead of the 0th term. All right, it's calling the base first, one step. All right, but it's really not, but we're going to do it anyway. All right, so really nothing's changed here except I've got 105 minus 7.5 every step I take. But now every step I take, we don't want to change on the first step, so we say n minus 1. Look, if I plug in a 1, n minus 1 is 0. 0 times this, my starting position of 1 is still 105. But that means I still have to take 14 steps, so we're going to make this from 1 to 15. That allows us enough room, our domain allows us enough room to get those steps, those 14 steps. What about a recursive? Well, if I was going to do a recursive, and it was my 0th term that I started, this guy starts at 105. All right? And then it says, hey, to find the output of this, of n, I have to know the step right before this and then subtract 7.5. To get your position, find the position right before this. If this was 3, 3 minus 1 is 2, and then subtract 7.5. Subtract your rule. And this would be, right, from 1 to 14. That's the only steps we're taking because we know the 0th step. We don't need that. We're only taking steps 1 to 14 here. Well, on this one, what if I have f sum 1? Well, that's still going to equal 105. It's just saying, hey, let's just call that first position the number 1 instead of 0. Well, f of n equals my previous step still. Nothing's changed here. Minus 7.5. The only thing that changed here is this. All right. I can't take that first step. I have to start on 2 and go up to 15 to make sure I have all my positions. And I should have a less than or equal to. All right. So this is a little weird. It's not crazy hard, and I think how many we've taken, looks like 7 minutes, and let's at least look at this. We're gonna go here. I don't think this next one will take very long. I'm gonna try to get through both of these next 2 pages in a single video, but we're gonna pause here and then we're gonna apply what we did, and we'll use these rules up here. All right.